All right, I'll give it a few more seconds, maybe 5 more, see if anybody more is coming. Apparently not. Okay. So what part of this has to be secret? The key is the only secret typically. The military sometimes likes to keep the algorithm secret too, but Kerckhoff's principle is the only thing you really need to keep secret is the key. All right. Which one of these is the weakest? Okay, the Caesar is of course the weakest. Which one's the most difficult to use? It's the problem. One-time pad is great, but too expensive, too hard to use. So which one allows messages of various sizes to be encrypted? That's the mode of operation, which we're going to get into a lot more later. It's different than the system. The system encrypts stuff, but the mode of operation is how you deal with message size, which turns out to be a big problem. So we got Caitlin, which I can't spell at all. All right, and then looks like Warren Lee, that looks like a real name. And then we got Dude, which I'll have to tell me who they are. It ain't gonna get their points. But anyway, let's go back to the slides. We're good, we got time to carry on here. So, all right, so we'll talk about the security of these systems. And in order to define the security of a crypto system, you have to do attack modeling. This is true of all security. There's no such thing as perfect security or bad security. You just have to talk about threat modeling. You have to say secure against what kind of attack. And then you decide what kind of attacks it can stop, and then you decide if it's acceptable to you that it stops those attacks, but it doesn't stop some other attacks. Like, for example, as we just saw in the news, the nation states have got stuff that will just take over your iPhone. So if you think you're going to stop a nation state attacker, you've got a serious problem. Then you're going to have to take all your stuff off the internet entirely or something. Most of us just accept that nation states can hack into our stuff, and they're not in our threat model. I don't think I'm going to stop the NSA or the Russian government from getting in my phone. I'm content to just stop the criminals out of my phone and assume that I'm not important enough for the government to attack. That's threat model. Yeah.
That's expensive too, isn't it?
That's what?
You know, those kind of attacks.
Yeah.
I mean, government's paying for it.
Yeah.
But those attacks are pretty expensive. So
yes.
It kind of makes sense that you, as John Doe or Jane Doe, really don't want it.
Yes, that's exactly it. And what you said, the attacks are expensive. So if the NSA has to pay for like James Bond to hunt me down and hack my phone, they're not going to do that unless I'm really plotting to kill the president or something. I'm probably not important enough, and that's the point. That's what you do. You decide what is the real threat, and then you protect yourself against the real threat. Otherwise, you're like descending into paranoia where you're running around hiding from scary threats that you can't stop, and then your life is nuts, you know. So you have to accept there is some risk, and I'll take certain risks. Like the NSA and the Russians might hack me, and I just blithely go through my life as if I didn't care, because it's not possible for me to stop them, so I just don't worry about it. Of course, the risks change. That's why you can just do nothing and be foolish, but you can also do risk management, where you make a calculated decision of which risks are acceptable and which risks are not acceptable, and you spend your effort on them. Anyways, that's very important. So this is threat modeling, helps you decide how to design ciphers, and it helps your users decide whether they should use something. You should rate a cipher not by is it secure or not, but by more precisely what attack will it stop. And then you can decide whether it's appropriate for your use case or not. So here's a typical one, right? The XKCD, the laptop's encrypted. You could build $1 million to crack it, or you could just hit the guy with a wrench till he gives you the password. I mean, and this is the point. There is no perfect system. There is a way to get in your stuff. if you use a perfect encryption, they can just stick a camera in your house to record the keypad while you type it. And then it doesn't matter about your encryption, you know, or they can bribe the person at the other end into telling them or something like that. I mean, there's always a way in. The only thing cryptography can do is force them to use another way to get your stuff. That's all you can ever do. So, all right, this is Kerckhoff's principle. The key is secret. The cipher is not secret. Most cryptographers agree that this is the right policy. Make the algorithm public and a known algorithm where everybody can understand it and test it until it's really strong and all secrecy is in the key. Some people think you should keep the algorithm secret too. Most people have discovered this is a terrible idea because if the algorithm is secret, it probably is stupid and you don't know that. If it was public, you could have the benefit of all the cryptographers and mathematicians in the world testing it until you know it's really strong. Your secret one is probably actually making a mistake that someone else made 200 years ago, and you don't know that because you didn't let the mathematicians analyze it. The only people that have the guts to use secret things and still feel secure is the military and fools that don't know what they're doing. This is why if you buy a commercial product and they won't tell you what the algorithm is, you should not buy it. Because unless they are very unlikely to be smart enough to have a cipher that is actually better than a public one. It's far more likely that what they have is something inferior and they are hiding that from you. Yeah?
Well, there's hardware limitations and then software for human limitations, right?
Well, sure, but they should tell you what the algorithm is. And it should be something normal like AES or DES or RSA. If they say, we invented our own algorithm, then by Skype, for example, Skype had an algorithm, nobody knew what it was, and the US military or the NSA offered $1 million for anybody that would hack into Skype and tell them what it was. And then Microsoft bought them and they revealed the secret algorithm and it was AES. It was not anything miraculous. That's what, so I mean, the only two choices if they won't tell you the algorithm, it's either AES or it's not. And if it's not, you're screwed because it should be. And the point is, if it's going to be strong, it should be one of the known strong ones. Whatever else they've got is not going to turn out to be as strong as the known strong one. Anyway, that's the general belief people have. Of course, notice this is also not like mathematically proven true. This is just sort of a rule of thumb, a conventional wisdom. A lot of cryptography is not all that perfect. The math makes it look good, but there's a bunch of parts you need to just sort of guess like you would anywhere else here. So here's how you can test cryptography. The simplest way is a black box model. This is what you normally think of. The only thing the attacker has is the ciphertext, like they're reading network traffic on the internet that's already encrypted. That's all they have. They don't have any ability to go inside your machine and don't understand how it's wired up. They can't measure the electric power you're consumed or anything. All they can do is see the output coming out. All they have is C. Then that's a ciphertext only attack, and that is the normal one you think of. You encrypt it on my machine, then I send it over the wire. The attacker can read the network traffic on the wire, but nothing else. A known plaintext attack is where they actually know some of the plaintext and they can see the ciphertext also. This, for example, is WEP. WEP encrypted wireless traffic. And it turns out if you actually open Wireshark and look at wireless traffic, a bunch of it is identical ARP packets. Where is 192.168.1.1? Tell 192.168.1.101. A whole lot of packets are identical for most of the bytes. And you can tell them from the others by their size. So in fact, you do know the plaintext for a bunch of that traffic. So known plaintext is often within your grasp. When people might think you can only see the ciphertext, you can in fact guess quite a bit of the plaintext. And then there's chosen plaintext where you can actually force it to encrypt input you put in. And then you can carefully choose input that pumps out information about the key. And then sometimes there's chosen ciphertext attack where you can feed in data that goes both ways. And those, of course, give you more possibilities of getting in. So gray box models are where you not only can look at the inputs and outputs, but you can actually look inside the calculation and learn something. So you can tamper with it. A side channel attack is where you measure something else, like the radio emitted or the timing or the power consumption of the process. And that's a non-invasive one where you measure something. And then there are invasive attacks where you actually alter the hardware. There was an RSA attack that broke into RSA 2048, I think this way, where what they did was they said sometimes processors drop a bit because of cosmic rays. It's actually, processors have so many bytes on them now, this actually happens fairly often, that it drops a bit. And they said, we're going to simulate this. If you were to just harvest the data and get the ones where it dropped a bit, you could eventually deduce the key, because dropping a bit halfway through a calculation does not have a random effect. It has an effect that depends on the key. And you can deduce the key from some of those dropped bits. So to test it, they lowered the power supply to the processor to where it was less than 5 volts, to where the processor started dropping bits. And they found that they were able to do RSA encryption. And by the time they got it to about 120 defective encryptions, they were able to totally deduce the key, because they had dropped 1 bit during the calculation and they were able to backtrack and figure out what that meant about the key. So that's an example of this. You could also, like they broke into Microsoft's BitLocker at Noisebridge, they dissolved the key with acid and reached in with a thing to measure the voltage going down one of the pins to find the key hidden on the secure element. These are the kind of things you can do if they have the actual ability to get at the hardware and mess with it. That's another threat model. So here's some security goals. Indistinguishability would mean that your ciphertext is indistinguishable from a random string and has no patterns. Non-malleability would mean you cannot take the ciphertext and use it to create other valid ciphertext. Like, for example, the Caesar cipher, if I wanted to just change a message, I could leave some of it the same, and I could change some letters over here, and I might be able to add the word not to it or something. You know, I mean, a lot of it can remain the same. And we're going to do a few attacks like that as you go ahead, where we're able to modify ciphertext into other ciphertext to our advantage without knowing the key. That's what the padding oracle attack does. You can forge a message even though you don't have the key. That's a failure of malleability. That's failure of non-malleability. So here's an example. Indistinguishability against a chosen plaintext attack is semantic security. This means even if you feed into identical plain text, you get different ciphertext. This is what you want. So double letters do not turn into double letters in the ciphertext. They get scrambled. This is what you want. Then there's asymmetric, and we're going to do various techniques later that test this. And then asymmetric encryption is what I mentioned. This is the new thing, which is awesome. This is what solves the key distribution problem. You do not have to move a secret. Every person makes a private key and a public key, and they tell everybody the public key and they never tell anybody the private key. Now you can receive secrets. Anybody that wants to send me a secret encrypts it with my public key. Nobody on earth can open it except me with my private key. I have a secret and I never tell anybody. The old system, you have this thing called a shared secret, and that's an oxymoron. If you've shared a secret, it's not really a secret anymore. How do you know that the other person didn't give another copy to a third person? You don't. So you don't really know who you're telling that message to. But in this system, it's not a problem. I have a secret and I never tell anybody. So I can really know under my control that nobody stole my secret, and to my degree of confidence. And that's what we're using now. We use this on the internet. We use public key encryption, which is a new technique. And it's very powerful, but it's going to go the way of the dodo bird, the current systems with quantum computers. But that has not happened yet. So right now, because quantum computers are not working very well yet, this is actually quite secure, the current versions of it. Anyway, then the other problem is sometimes people use ciphers to do more than encrypt text, and this gets you back to threat modeling. It was designed to stop a certain kind of attack, but you might be doing something else, like authenticated encryption, where it's not enough to just know it's encrypted. You also want to know who sent it. And you'd like to take their presentation of valid ciphertext as proof of who they are, in addition to transmitting the message. So this is authenticated encryption or authenticated encryption with an associated data. And as we'll see, it takes different systems to do this. And if you just sloppily use a system that was designed just to deliver messages and interpret it as proof of identity, you often get in trouble because it wasn't really designed for that. Anyway, then there's format preserving encryption. This is the new breaking thing. If you think about Dropbox lets you have 2 gigabytes of storage for free. Now, how can they do that? The reason they do that is because everybody stores the same stuff. Copies of an MP3, Word files, images they've downloaded. In fact, 99% of all that data is just duplicate of somebody else's data. So they just store 1 copy of the data. So they don't really need to have 2 gigabytes for every customer. They really need maybe 5% of that or 1% of that, and they just point you to the other file. And that's fine as long as you have no privacy. But if you were to encrypt that stuff for privacy, then you'd have 1,000 copies of the same MP3, and they'd have to store 1,000 copies on the server. So people have tried to develop crypto systems where you can encrypt stuff, and yet you can still tell if 2 things are identical at the other end. Now, format preserving encryption is one version of this, where because you have a database designed for unencrypted data, like zip codes, you want to encrypt it, but you want to put it in the same database that only has room for a zip code. So you're going to keep the same format. The encrypted zip code will still have the same format as a zip code. The encrypted IP address will still have the same format as an IP address. That's one version of this, where you encrypt stuff, but you do not have to redesign your old database. But what's more fun is homomorphic encryption, where you can actually modify the encrypted data without decrypting it, or even search through the encrypted data without decrypting it. And these systems have been developed very recently, but they're so far insanely expensive and slow to run. This is sort of like magic, where you're going to preserve privacy and still be able to find duplicates and search through stuff, which would be like a holy grail of encryption, but we're not really there yet. And okay, searchable encryption, where you can somehow search through something even though you can't read it. It sounds impossible, but it's not quite impossible. It's just very impractical. But this is where some people would like to go. Then there's tweakable encryption, and this is why I just got a swag at this event. They gave me an encrypted flash drive that looks like it's 15 years old. And I know it's probably going to be vulnerable because there's a problem. The hardware, the official RFC specification for encrypted hard drives is pretty bad. It is not, you can encrypt a hard drive with just an AES key, and that would be fine, but then it wouldn't meet the standard. The standard says you have to encrypt a hard drive for multiple users, and each user has to have a separate key, and they have to have their own separate area of the thing. And this turns out to be very hard to do, and most manufacturers that attempt to do this foul it up and in fact ruin the whole thing. And here's what you've got here. Tweakable encryption is what you have here, where you feed in another number, like a customer number in, to your algorithm. Coming here is the tweak, so that even though areas are using the same key, there's some other number to make them different. So that's for things like encrypting hard drives, another level of confusion. So there's many things that can go wrong. You can have a weak cipher, like the Caesar cipher. Phones in 2G used the A51 cipher that turned out to be very vulnerable. It was vulnerable to a time memory trade-off attack, which means you could make a lookup table to do some of the calculation and make it so fast that you could do a brute force attack. The same thing happened to Microsoft password systems up through Windows XP. They used an old IBM system that was vulnerable to the same attack. Then there's the wrong model. The padding oracle was where a user submitted data, and if that data was correctly encrypted, that was taken as authentication. And the server would give you an error message that told you why decryption failed. It would tell you if the problem was that the padding failed or that some other thing failed. And that additional information turned out to be enough to ruin the whole thing. That's the problem. It was designed saying something like you only see the ciphertext. But if you see the ciphertext plus an informative error message, you suddenly know a little bit more. And even a little bit more can ruin the whole thing, shattering it like glass. So we'll be doing that. I'm cracking into using that. And I got some more cahoots here. And we're up to the hour, so I think we're doing fine here. Let me find my second set of cahoots. There they are. All right.
Did you ever see that movie Ex Machina?
Yes.
There's a scene where the two guys are talking, and one of the guys is saying, telling him where he got all the knowledge.
Yeah, I don't remember that, but yeah.
And I was just thinking about that when you were describing all these possibilities. Given time, it's perfectly possible. Now, here we have that someone with enough money and obsessed enough.
Well, it's certainly true that almost every secret is for sale now. You can totally get it. Like they leaked all the OPM data about all of our military people, their weaknesses, their drug addictions, their security problems, just what you don't want the bad guys knowing. I mean, and certainly all the source code for every product has been available on Darknet for a long time. Yeah, it's certainly the case. That, and with all this is why the privacy people are real upset about all the proliferation of NSA spying and reading the email and putting cameras everywhere. So, you know, you're not really protecting all that data. It means that people can totally like find out everything about you and stalk you and stuff. That's the downside of it. The upside is supposedly we have better law enforcement. We can catch all the bad guys, but it's not entirely clear if that's really happening. You would like to think, for example, you catch everybody stealing money, painting it on the wall, doing a terrorist attack. They should also be on all this camera data somewhere, if you can find them. That's the good side of Big Brother. Anyway, I'll give it a few more seconds. All right. So, what do you need if you want to know if a cipher is safe to use? You need threat modeling. There's no such thing as safe. You have to say safe against what threat, and then you can talk about it. All right. Kerckhoff's principle doesn't say anything about the security of something. It just says the secret should be in the key. Threat modeling is what tells you if something's safe. You cannot say, give me something safe. You have to say, what is your situation? What would be safe enough for you? Then we can talk. That's why when the blockchain voting system advertised themselves as 100% secure, I contacted them and said, don't say that. Say, what do you mean? I say, do you have any security people on your staff at all? You never say that. Nothing is 100% secure. This doesn't even exist. This is like 100% healthy, 100% perfect, 100% beautiful. None of this is true. You have to define your conditions and say, we are resistant to this attack. That's not 100%. Anyway, so what category is COA and KPA? What's that? Okay, those are black box models. That's a ciphertext only attack and the known plaintext attack. They're two different black box attacks. All right. And if you lower the power supply voltage to cause errors, what kind of attack is that? That's an invasive attack. You actually mess with the hardware. You know, you would like to hope that the bad guy can't do that. But for example, if you're testing something like a Cisco VPN concentrator or a voting machine, they can just buy one and take it apart. And that's what they did at DEF CON. And of course, they found that you could totally hack voting machines if you can buy one and take it apart and see what's in there. But that should be in your threat model because that is not out of the reach of the bad guys for commercial products. They could get one and mess with it. Anyway. All right, how about side channel attacks? All right, and that's a gray box model where you are not altering the hardware, but you are examining something other than just the output. All right, so we got more winners. All of them have strange names though. Man, food, and WITB world. So you guys will have to tell me who you are. I see some chat messages. Perhaps people are going to unmask their secret identities here. Okay, good. I got a name for man. All right, and I got WITB, good. All right. Okay, good. So I have at least a couple names. All right. And the last thing I want to do, we've been here for an hour, but I think I'll just go a little further and then do a little bit of math. I think we did the first two binaries last time. So we ought to do like maybe one more of them. If we do a little bit of it every time, it's the best way to learn math. That's my theory, which is I found to be true. And so if I go down to the binary games, which are here, we got down to this one last time, I think. And here's the lesson. All right. So that's looks like it's fitting on the screen all right. Let me, all right. So in base 10, 147 is 100, 4 10s, and 7 1s. So in base 2, it's 1s, 2s, and 4s. And if you count to 7, 1 1 1 is 7, 1 0 is 2, 1 0 0 is 4, and so on. Here's the nibbles up to 15. 4 1s is 15, 10 10 is 10, 10 11 is 11, because this is 8 plus no 4s plus 2 plus 1. And if you do bytes, you've got 1s, 2s, 4s, and 8s, and then 16s, 32s, 64s, and 128s. So that is one way to do it. This number here is there for 128 plus 16 plus 8 plus 1, and that's 153. So there should be a binary game for that in my Cahoots. Let me bring back my Cahoots. And go to my favorites. And there should be binary 2B. There we are, binary 2B. See how this looks.
I'm not familiar with this. Is this just for, schools, education, or is this
No, totally free to anybody. No, anybody can use it for anything. It's totally free, and now they're beginning to like try to get you to pay $1 a month, which I haven't done yet. But if they put up this thing, and you can put up different kinds of games like crosswords and stuff. It's really very nice. I just don't know how they're making enough money to survive. It's from Europe, and I think they're still burning through their seed money, is what it looks like to me. At some point, they're going to make me pay, I would hope. There's no what? No, there's no ads. Now, when you start, they try to say you should pay $1 so you can like sort your Cahoots into folders. But that hasn't motivated me yet. They also say if you pay them some money, you could put your company logo in the background and stuff. But it looks to me, it's a great product, but I'm worried about how they're going to fund it. I'd be happier if like Microsoft bought them or something. Anyway, we'll see what happens. It is a great product, though. So let's try these. So what is that mess in base 10? One with 7 zeros after it. Yeah, good. The 0B in front means binary. I'm using Python notation. So that's 128. All right. It can't be 256. 256 would be bigger than a byte. So this is 4, and this is another 4. 256 would be 9 digits, 9 bits, and it's only 8 bits. All right. What's this mess in base 10? It's actually pretty easy, but anyway. 10, 10, 10, 10. I like the music. They're clearly paying for people to develop a lot of different music. Okay, that's 170, which you will, I might as well say this is very easy to do because I told you before 10, 10 is 10. And this is another 10 over here. What all you do is multiply the second byte by 16. This is where we're going to get hexed. You have the left nibble times 16 because these are 4 shifts to the left. Shifting something 4 times to the left is multiplying it by 16. So this is 10 times 16 for 160, and this is another 10 for 170. So that's right. Once you learn hex, you can just read these right off of there, which is really slick. But right now, if you're doing it the hard way, you do 128 plus 32 plus 16 plus 2, and that'll get you there, but it'll take a while. And you have to, and I can't do it in my head very well. Anyway, hex makes it easy to do in your head. The other way, you got to have a little piece of scrap paper and some patience. Anyway, how about this one? Okay, 5 people are faster than me. Okay, this is 16 plus 1, 17, a popular answer anyway, good. And how about this one? Okay, 3 people faster than me. Okay, it's 240, which is correct. There are a lot of ways to make it fast. The way I did with 15 times 16, you can also take 255, which is all ones, minus 15, which is the 4 ones on the right. There are many ways to get here. You could also do 128 plus 64 plus 32 plus 16. They should get you to 240. All right. And I guess I got one more of them. Okay. Okay. 2 people faster than me. Okay, that's 47, because if you add 1, this rolls over and turns into 1, 1, which is 3 times 16, 48, which is 32 plus 16, if you like, another way to get there. So it's 48 minus 1. That's one fast way to do it. Anyway, let me record these winners, and I think I'll try the next one tonight, and we may repeat it next time, because I'm not getting unanimity here, but I think it might be worth looking at anyway. You may just take a look at hex, because I've been already anticipating it. Hex is the easy way. So let's take a look at hex. Here's hexadecimal. So if you count to 15, you go from 0 to 1111, and in hexadecimal, you just take 1 character to encode this. So 0 through 9, it's the same as base 10, and then you use the A, B, C, D, E, and F for 10, 11, 12, 13, 14, 15. So 1 character is a nibble. That's hex. That's all you need. And you get used to this, and after a while, you get used to knowing that A is even and B is odd, and C and E are even, and D and F are odd. It seems crazy, but after a while, you just get used to it. And now that you know that, 4 bits is a nibble, and that's 1 character. The nibbles go from 0 to F. That's it. And because of that, 8 bytes is 2 characters, always 2. The left nibble is 1, 0 through F, and the right nibble is 1, 0 through F. So the easy way to do this, the old way we did this was 128 plus 16 plus 8 plus 1 to get 153, and that's for the birds. That is too much work. The easy way is this. You take the left nibble, which is the number of 16s, and the right nibble is the number of 1s. The left nibble is 9, 8, 4, 2, and 1. This is 9, and the right nibble is 9. So this number is 9 16s plus 9. That's 140. That is the easy way to do it. And multiplying by 16 gets easier. There really are only a few of them. When I started, I'd make a little chart of the 16s here on a piece of paper. So that's the easy way to do it with hex. And let's do some hex, which I should have a Kahoot for. That would be binary 3A, hex. All right, there we go. That's why everybody uses hex for assembly language and Wireshark traces and disk sectors. Hex is the right way to write down binary so humans can read it and remember it. It is the way, it is in between binary and decimal, so you can easily go either way. It reminds me, I didn't get dinner yet either. All right, I'll wait a few more seconds. Maybe everyone's given up. Scared them away with terrible binary. Wait a few more. Blood Mage is back anyway. They're still coming in. Okay. Shouldn't be afraid of hex. Hex is actually much easier than the last one. I'll give it another 5 seconds. All right. So what's that in base 10? That's a hexadecimal number, 10. 0x means hexadecimal in Python.
Oh,
Yeah, it's not binary. 0b is binary. 0x is hexadecimal. So that is 16. Yeah, you might think it was 2, but it's 16 because that's hexadecimal. That's fine. That's how, all right, so how about this one? 2-1 in hex. This one you can't misunderstand because there is no 2 in binary. Okay, that's 33. 2 16s plus 1. How about this one? AA. And you convert it to base 2, not base 10. That's it. A is 10. So the left nibble is 10 and the right nibble is 10. 10, 10. Good. Everyone got that? Glad to see it. All right. How about this one? E1 in base 10. Okay. 3 people faster than me. Okay, it is 14 times 15 plus 1. And 14 times 15 is 10 times 15 for 150 plus 4 times 16 for 160 plus 64. So that's 224 plus 1. It's a little bit annoying to take 14 times 16, but anyway, that's it, 225. Now all over the place. Anyway, that's as far as we're going to go. We'll do more of this next time. But anyway, so our blood mage has won twice, but I don't know who they are, although I have an idea. Actually, blood didn't win yet today. Okay, so blood wins now. Blood won last time. And hungry. And C, so you guys aren't going to get your points unless you tell me who you are, however.
I was dude and dude 3.
You're dude and dude 3. Oh, okay, good. Good, so you won twice, okay. Right. Right, I remember your name, okay. All right. So I took care of that. Caitlin's actual real name, that I can handle. Warren's a real name. Any other, like food and stuff? Oh, okay. I have a message. Oh, good. Thank you. This may be another person revealing their secret identity. Hungry. Okay, good. Hungry is Richard L. Good. Okay, good. And the other people I already knew. All right, so I have several of them. Blood never told me who they are, and C never did, and the face never did. But anyway, we'll see if any people want to bring it up here. Anyway, I think I'm going to stop this. I'll just clean up and go up to the lab in 214 if anybody wants to work tonight. So you can stick around and want to work here, but if you want to do your work from home, that's fine too. And I'll see you next week. All right.